Assalamu alaikum. Today we are starting with a new chapter of your textbook, and the first topic which we are covering today is sampling theorem. Sampling theorem will cover both CLOs 1 and CLOs 2, and it is 6.1 of your textbook. So here we will cover different topics. The main contents of today's lecture are as follows. First, we will look at Fourier transform of rectangular pulse. Then we will study an important principle which should be remembered at every stage while performing sampling. Then we will start with sampling theorem. We will look at the statement of sampling theorem, and then we will perform different cases of sampling. After that, aliasing will be discussed, and then we will study that how we can avoid aliasing, and at the end we will discuss signal reconstruction when sampling is performed. First, start with some previous knowledge. We should know the Fourier transform of a rectangular pulse. If g of t is a rectangular signal rect of t in time domain, then which can be defined like this: the amplitude of this signal is 1 between minus tau by 2 to tau by 2. So from here you can observe that g of t, the total width of this time domain rect is tau, and the half of this tau spreads on the positive side, and the other half is also spreading on the negative side, while total width of this signal is tau t by 2 plus minus t by tau by 2, so it will become tau, and the amplitude of this rect is 1. If we apply Fourier transform on this rect or gate signal, then we get a sinc function. This sinc has amplitude equal to tau, which is basically the total width of time domain signal, and the first zero crossing of this sinc is at 1 over tau, second zero crossing is 2 by tau, and third zero crossing is 3 by tau, and so on and so forth. So this is the relationship, an important relationship which we must know before starting the sampling theorem, that if we apply Fourier transform on rectangular signal, then we get a sinc function, and if we apply Fourier transform on sinc function, then we get a rectangle signal. So just have a look at how we can derive the Fourier transform of rectangular signal. Here we have x of t, which is equal to 1 between minus t by 2 to t by 2, otherwise it is 0. So if we apply Fourier transform formula, and then it will become integration minus t by 2 to t by 2 e raised to power minus j omega t, x of t is equal to 1. So at the end, so if after performing integration, we get sine omega t by 2 over omega by 2, and if we look at it carefully, then we know that it is basically a sinc function. So another principle which should be remembered is that an absolutely band limited waveform can't be absolutely time limited. Band limited waveform means the waveform is limited in frequency domain, whereas time limited means that the waveform is limited in time domain. So it is not possible that a signal is limited in both domains. If signal is limiting in frequency domain, then it will expand in time domain, and if it is expanding in frequency domain, then it will be limited in time domain. You can observe this principle from this figure. Here we have time limited rectangular signal, but if we apply Fourier transform on this time limited signal, then we are getting a sinc waveform which is which is not a band limited signal, but it is basically continuous in nature and moving from minus infinity to plus infinity. So this is not band limited, but here it is a time limited signal. So you will get either time limited signal or you can get band limited signal. It is not possible to get both time limited and band limited signal at the same time. So let's start with sampling theorem. It is basically a process to convert continuous time signal into discrete signal. So here we have continuous signal, and at the output of sampling we will get a discrete signal in time domain. Sufficient number of samples must be taken so that the original signal is reconstructed properly. Samples are to be taken in such a way that at the output or at the receiver we should be able to reconstruct our signal. Number of samples to be taken, how many samples are to be taken, it is basically depending on signal frequency. So the sampling frequency will be depending on the message frequency. There are different types of sampling. The first one is ideal sampling, second one is natural sampling, and the third one is flat top sampling. We will have a look at these types later in this lecture. So first start with the statement of sampling theorem. It can be given as a band limited signal of finite energy which has no frequency component higher than FM Hertz. It means the message signal has a frequency equal to FM Hertz. So this band limited signal can be completely described by its sample values at uniform intervals less than or equal to 1/2 FM seconds apart. So this is basically our definition in frequency in time domain, because we are talking about interval. Now we can define it in another way, like a band limited signal of finite energy which has no frequency component higher than FM Hertz may be completely recovered from the knowledge of its samples taken at the rate of 2 FM samples per second. So Fs should be greater than or equal to 2 FM. It means if Fs is the sampling frequency, then this sampling frequency should be greater than or equal to 2 times of message frequency. If message signal's frequency is 5 kilohertz, we are supposing it that the FM is equal to 5 kilohertz, then sampling frequency should be equal to 10 kilohertz. 5 into 2 is equal to 10 kilohertz. Means sampling frequency should be greater than or equal to 10 kilohertz if FM is equal to 5 kilohertz. The interval between two samples is denoted as TS. Here TS is basically the sampling interval. So we know that frequency and time has inverse relationship. So Fs is equal to 1/TS. So if we are assuming that there is a signal x of t in time domain, and then in frequency domain it should be band limited, because in time domain it is not time limited. So in frequency domain it will be band limited, and it has a frequency equal to FM. We know that here we are representing it with angular frequency, so we can say that it is between omega m to minus omega m. Now x of t has no frequency components beyond FM, so we can say that x of omega means x of the frequency domain version of x of t, which is x of omega, is equal to 0, and when it is equal to 0, when omega is greater than omega m. So when the value of omega is greater than omega m, then x of omega will be 0. So if we apply x of a Fourier transform on x of t, then we are getting its frequency domain representation. We are not going into detail that what is the actual shape of x of t. It is just an assumption that this is some signal in time domain, and we are getting its frequency domain conversion. Now for sampling, what do we need? We basically need pulse train. Pulse train is in such a way that pulses are coming after every t seconds. So if first pulse is at 0, then the next pulse will be after ts seconds, and then the next pulse will be at 2 ts, and after that 3 ts, and so on. So mathematically the Fourier series expansion can be given as, we know that this is a periodic signal, so we will represent it with the help of Fourier series. It can be written as 1 over ts, which is basically the difference, time difference between two pulses. And then we have 1 plus 2 cos omega st plus 2 cos 2 omega st plus 2 cos 3 omega st. So it is 1 omega s is for 1 first pulse, then 2 omega s is for this 2 ts, and then 3 omega s is for this third impulse. Now the sample signal can be written as g of t is equal to x of t into del ts of t. So what we are doing, we are basically multiplying x of t, which is our time domain signal, and we are multiplying it with impulse train, and at the output we are getting g of t, which is the sample signal. This is very important, that how we are getting a sample signal. We are getting a sample signal by multiplying x of t, time domain signal, with impulse train, and at the output we are getting g of t. So this g of t is the sample signal, and this dotted is signal is m of t, which is to be sampled. And after multiplying m of t or x of t with the impulse train, we are getting these samples, and these samples are present at 0, ts, 2 ts, minus 2 ts, and up to infinity. Now in mathematical terms, we can say that x of t is being multiplying with impulse train. This is the Fourier series representation of impulse train. If we perform Fourier transform on this equation, then we get g of t equal to g of omega, and then x of t will be multiplying with these factors, and in frequency domain we will get x of omega, plus when x of t will be multiplying this 2 cos omega st, it will be converted into x of omega minus omega s plus x of omega plus omega s. So we know that this omega cos omega s has 2 impulses in frequency domain. One will be at omega s and the other will be at minus omega s. Similarly, this cos will again has 2 impulses. One will be at plus 2 omega s and the other impulse will be at minus 2 omega s. So when this x of t will be multiplying with these impulses, it will be shifted. The Fourier transform or the frequency domain representation x of omega will be shifted at omega s, minus omega s, 2 omega s and minus 2 omega s. This is represented in graphical form here. This is g of omega. Omega is on x-axis and g of omega is on y-axis. So this is x of omega, which is the Fourier transform or frequency domain representation of x of t. Then we have omega s. This Fourier x of omega minus omega s is showing that x of omega is being shifted at omega s, and then x of omega plus omega s is showing that x of omega is being shifted at minus omega s. So from here we will get signal at 2 omega s, and from here we will get signal at minus 2 omega s. So to avoid overlapping, we can say that if this part is omega s and this side is omega s minus omega m. Then to avoid overlapping, omega s minus omega m should be greater than omega m. If it is less than omega m, then it will have overlap with omega m. So to avoid overlapping, omega s minus omega m should be greater than omega m, and from here we get the sampling theorem that omega s, that is sampling frequency, should be greater than 2 omega m. So if we want to reconstruct x of t from g of t, because we know that g x of t is our input signal and g of t is our sample signal, we must be able to recover x of omega from g of omega. Obviously it is only possible if there is no overlap between successive cycles of g of omega. These are successive cycles of g of omega, and if these cycles are overlapping with each other, then we are not able to reconstruct our signal at the receiver side. But if there is a appropriate difference or gap between these two cycles, only then we will be able to retrieve our message signal or x of t from the sample signal. Thus it requires fs or omega s should be greater than or equal to 2 omega m, or in time domain we can say that ts should be less than or equal to 1 over 2 fm. So at this stage we can summarize our discussion that as long as sampling frequency should be greater than or equal to 2 fm, g of omega, the sample, will repeat periodically without overlapping. As we observed on previous slide, that if the successive cycles of g of omega are far apart, then we will be able to retrieve our message signal. So if fs is greater than or equal to 2 fm, then g of omega will repeat itself without any overlapping. And at the receiver, if we place a low pass filter which has cutoff equal to omega m, then we can extract our original information. So here we have basically 3 cases, depending on the choice of sampling frequency. If sampling frequency is greater than 2 fm, then we can say that to avoid successive cycles and there will be no overlapping, so it will be the scenario that all cycles are far apart and there is no overlapping. If sampling frequency is equal to 2 fm, then successive cycles will touch each other. They will not overlap each other, but they will touch each other. And then if a sampling frequency is less than 2 fm, then successive cycle will start overlapping with each other, and hence a reconstruction of the original signal will not possible. Therefore, for reconstruction without distortion, because this is basically distortion and we need to avoid this, otherwise we will not be able to reconstruct our original signal. Thus for reconstruction of the original signal without distortion, we want to select sampling frequency either greater than 2 fm or equal to 2 fm. So we can merge both of these conditions into one condition, that fs should be greater than or equal to 2 fm. Now if fs is equal to 2 fm, we can say that this sampling frequency is basically our Nyquist rate. Since sampling theorem was proposed by Nyquist, so we also say it call it Nyquist theorem. So if fs, sampling frequency, is equal to message 2 times of message frequency, then we say that this is Nyquist interval, Nyquist rate. And if ts is equal to 1 over tm, then ts is called Nyquist interval. These 2 terms are very important, and you will repeat these 2 terms to solve your numerical problem. So fs is Nyquist rate and ts is Nyquist interval. So now we will study what is aliasing and how wrong selection of sampling frequency results in aliasing. This aliasing is basically a result of undersampling. It means if we are selecting fs such that it is less than 2FM, then it results in aliasing. Aliasing, which is also known as overlapping. Here, two successive samples or cycles are basically overlapping with each other. Now these successive samples are overlapping and there will be distortion, which is known as aliasing. Thus it is not possible to recover original signal. This is the main drawback of aliasing, that at the receiver side we are not able to recover our signal. Now the question arises, why signal recovery is not possible? It is because if we use low pass filter to recover the signal, there is a possibility of distortion, because low pass filter has a sharp cutoff and at the edges we will have signal which is a combination of two successive cycles. And if we look at the inward side of this cutoff, then we have cycle 1 and then we have successive cycle also. That's why it is not possible to completely separate these two cycles, because they are overlapping with each other. So it means aliasing should be avoided no matter what. That's why now the question is, how can we avoid aliasing? The first way is a sampling frequency should be greater than or 2FM. Obviously, when these successive cycles are at a distance from each other, then there is no possibility of aliasing. But if they are very close to one another, then there is a possibility that they will start overlapping with one another. The second way to avoid aliasing is to pass your message signal through a filter which is known as anti-aliasing filter, band limited filter, or pre-aliasing filter. The purpose of this anti-aliasing or band limited filter is that it converts band unlimited signal into band limited signal. Now when the signal is band limited, then it is not possible that it will affect the neighbor signal. So to understand that how pre-aliasing filter works, we can observe that here we have x of omega, which is a signal with frequency components approaching to infinity. This x of omega is a signal which is basically moving from minus infinity to infinity. Now if FM is so we can say that the message signal, this message signal has frequency which is basically approaching to infinity. Now to avoid aliasing, we know that sampling theorem should be followed, which states that Fs should be greater than or equal to 2FM. So if FM is approaching to infinity, it means Fs, sampling frequency, should also be equal to infinity, which is not possible obviously. Now to avoid aliasing, what we are going to do, we will convert band unlimited signal x of omega. We know that this is in frequency domain, so we will say that this is band unlimited, its frequency range is unlimited. We will convert this x of omega into band limited signal by reducing the FM. So by band limiting or by passing this signal through low pass filter, we will reduce the omega m or the message signal frequency. So it is only possible by passing original signal through low pass filter before sampling. So before sampling, we will pass this band unlimited signal through a low pass filter. This we assume that this low pass filter has transfer function like this, and it has cutoff frequency equal to omega m. Now when this omega m will passes through h of omega, we will get this band limited signal. So now we can say that at the before LPF we have band unlimited signal, and after LPF we have band limited signal. Such a low pass filter is known as anti-aliasing filter. In this way we can avoid overlapping of successive cycles, because we have limitized our signal in frequency domain. So these are a few problems. However, I will discuss these problems in live session. For now we will just skip it. Up till now we have studied what is sampling theorem and how aliasing affects our signal if we don't follow sampling theorem, which states that sampling frequency should be greater than or equal to 2 FM. So basically, if we are not following sampling theorem, then our signal reconstruction is affected. So at this stage we will study that what is a signal reconstruction and how we can reconstruct our signal from the sampled signal. So reconstruction of continuous time signal x of t from its sample is known as interpolation. This signal reconstruction is also termed as interpolation. So the signal reconstruction or signal interpolation means you are getting continuous time signal from the sampled version. X of t can be recovered by passing the sampled version through low pass filter. What we are going to do here is that we will pass the sampled signal through low pass filter. If we assume that the transfer function of low pass filter, which is also known as interpolated filter, is expressed like this, then h of omega is equal to ts into rect omega over 4 pi fm. So h of this is the transfer function or h of omega of reconstructed signal. The cutoff is omega m, which is also equal to 2 pi fm, and on the other side it is minus omega m and minus 2 pi fm. So this is the transfer function, and in mathematical terms it can be represented like this, because we know that this is a rectangle, this is rect. Now we know that sampling is basically, in mathematical terms, sampling is a multiplication of x of t with impulse train, and this g of t is then equal to 1 over ts into x of t plus 2x of t cos omega st plus 2x of t into cos 2 omega st up to infinity. So this is basically these cos terms are present in the equation because of this impulse train. Now what we want, we are targeted or required signal is g of t. We basic is g of t. So we know that 1 over ts into x of t. So g of t is the sampled signal, and we want to retrieve x of t from this sampled signal. So LPF should have gain ts. This ts is the Nyquist interval. Thus h of omega is equal to ts, and if we take inverse Fourier transform, then we know that h of t is equal to f inverse h of omega. So at this stage what we are doing, we are basically trying to find the time domain representation of our low pass filter or our interpolated filter. So this is this is our filter in frequency domain. We are applying inverse Fourier transform so that we may get its time domain expression. We know that rect and sinc has a relationship. So if we are applying inverse Fourier transform or Fourier transform on rect, then we get sinc signal, and so we say that h of t is equal to ts into 2 fm sinc 2 pi fm into t. So this is the frequency time domain representation of our low pass filter. Now we know that samples are running at Nyquist rate, so we know that ts is equal to 1 over 2 fm, and if we shift this 2 fm on the other side of the equation, then we get 1 at the right hand side of this equation. We can replace this ts into 2 fm with 1, and our equation 1 will become 1 into sinc 2 pi fm into t, and h of t is equal to sinc 2 pi fm into t. So this is the low pass filter of our signal of our so from figure it can be observed that h of t is equal to 0 at all Nyquist sampling instants, except t is equal to plus minus n over 2 fm. So so the h of t, value of h of t is 0 except at t is equal to 0. When the value of t is equal to 0, then we have main loop. Otherwise, other zero crossing we have h of t equal to 0. So this is first zero crossing, which is equal to 1 over 2 fm. This is second zero crossing, which is equal to 2 over 2 fm. This is third zero crossing, which is equal to 3 over 2 fm. So in this way, at all Nyquist sampling instants, we are getting 0 except at t is equal to 0. When sample signal g of t is applied at the input of this filter, then output will be x of t. So at this stage, we know that g of t was the sample signal and we wanted to get x of t, which is a continuous time signal. So this g of t, which is discrete time signal, we will pass it through low pass filter, and at the output we will get x of t. So far we have converted the frequency domain representation of low pass filter into time domain, which is a sinc signal. Now g of t is comprised of many samples, so each sample will produce a sinc pulse. We know that corresponding to each sample we will have sinc pulse. And now at the output of this low pass filter, we will add all sinc pulses, and then we will get x of t. You can understand this concept from here. These samples are representing g of t, and each sample has separate sinc pulse. Now when all these sincs are adding, then we are getting our reconstructed signal x of t. So for each sample of g of t, we have g of t is equal to x of ts into del of ts. So for kth sample, we can say that this equation can be written as g of t is equal to x of kts. It is showing that it is the kth sample of signal x of t, and t minus kts is showing that it is the kth sample of impulse train. Now kth sample of g of t passes through the low pass filter h of t, and we know that in time domain it will convolve with each other, and through the convolution property of impulse train, we get that it will convert into this h of t will convert into h of t minus kts. So x of t, for all samples of x of t, we can take summation, and x of t will be equal to x of kts into h of t minus kts. When we put the value of h of t, then it will convert into x of kts into sinc 2 pi fm t minus kts. So this is our final equation. It is showing that we have reconstructed or retrieved our time domain signal from discrete time signal. Here x of kts is multiplying with sinc, and these are impulses, so each sample signal will be multiplying with this impulse, with this sinc, and then at the output we are basically adding all these sinc pulses, and we are getting x of t. This is the final equation of our lecture, and it is also known as interpolation formula. So x of t can be any signal, and by using this formula we can reconstruct our signal. This is all for today's lecture. Thank you.